So today we're going to cover this document calculus 1 review. I don't expect this will take the entire 2 hours, so whatever is remaining at the end will become office hour in addition to the 3 o'clock, 4 o'clock office hour. Let's start number 1. Number 1, we have 5 limits. So on this final, if you have a limit, you can use L'Hopital's rule whenever you want if it applies. For these, I will use it only if we have to. 1a, limit as x goes to 1 over x minus 1 over x minus 1. So first, we try a substitution. And here, a substitution won't work because it gives a 0 over 0. But what we can do is simplify this expression. And what do we get? Well, let's, I'll go down first. Limit as x goes to 1. The numerator, denominator we'll leave alone. The numerator can be written as 1 minus x all over x. And now we can write this as a single tiered fraction. Well, we can write this as a single tiered fraction, 1 over x, or 1 minus x all over x divided by x minus 1, same as 1 minus x over x times 1 over x minus 1. So in particular, the denominator would become x times x minus 1. Something divided by 2 divided into 2 again is something divided by 4. But this 1 minus x in the top, we can factor out a negative and be left with an x minus 1 quantity, which will cancel with the other x minus 1. Limit as x goes to 1, negative 1 over x. Substitution now works. You get negative 1. Any questions about 1a? Okay, 1b. Limit as x goes to 1 of x cosine of pi x. Now, cosine is a continuous function, so we could apply a substitution argument if it works. What happens when we let x equal 1? Well, we would get 1 times cosine of pi. Well, cosine of pi is a number. What's cosine of pi? It's the x value over there, the x value over there, negative 1. So we get 1 times negative 1, which is negative 1. Any questions about part B? Part C, x squared cosine 2 over x. This is erasers. X squared cosine of 2 over x. Now here, we would like a substitution to work, but 2 divided by 0 is not a number. So we can't do a substitution here. And when we can't do a substitution, well, we're pretty much left with hoping we can use a squeeze theorem argument. And we have a cosine function, so maybe we can use a squeeze theorem argument. Because for the squeeze theorem to work, we need our function to be bounded above and below by 2 functions which have the same limit. And we can get there, well, we may be able to get there, by first observing that cosine of 2 over x is always between 1 and negative 1, wherever 2 over x is defined, which is everywhere but 0. What happens at 0 doesn't matter. Now, that function isn't the function in question. The function in question is this with an x squared on it, so let's put x squareds on everything. Put x squareds on everything, and now we have the function in question. We want the limit as x goes to 0 of that function. On this side, as x goes to 0, negative x squared goes to 0. On this side, as x goes to 0, x squared goes to 0. So what is in the middle will also go to 0. Let's say by squeeze. There. Since we applied the squeeze there. Any questions about that? Ooh, the erasers here don't seem to be working. They actually seem like they're dry rotted, but this one works fine. Okay, part D, limit as x approaches 0, right, 1 minus log of x. One minus log x. Now here, we can't do a substitution argument because log of 0 does not exist. But what we can do is maybe use the logarithm graph. So here, we have log x going through the point, what is that, 1, 0, either 0 is 1, so log 1 is 0. And now we can build the function in question. Take its negative, meaning make all y values negative, causes it to flip over the x-axis. Still going through 1, 0, so we have y is negative log x. Add 1 to everything. Lift the graph up 1 unit. That point is now at 1, 1. Here, we have a sketch of our curve, 1 minus log x. And we can see as x approaches 0 from the right, what x values are we looking at? We're looking at these. As x approaches 0 from the right, that keeps going up to positive infinity. You could have justified getting to positive infinity just from an observation using the first graph. But here, I'll just use the whole graph. Any questions about 1D? One E. Limit as x goes to infinity, 1 plus 1 over x, all to the x. Well, here we have x is in our base and x is in our exponent, and we're taking a limit. So if the limit through a substitution type argument gives a number, well, then that's our limit. But if not, we're going to have to introduce a logarithm to turn it into a product and then work from there. But here, as x goes to infinity, you get 1 plus 0 in the limit. The exponent goes to infinity. This takes a 1 to the infinity form. 1 to the infinity, not a number. But what we can do is use a logarithm, apply L'Hopital's rule, to figure out what this equals. So this equals, and to figure it out, we're going to do some side work. what are we going to compute? Limit as x goes to infinity of the logarithm of this quantity, because the logarithm will bring that exponent out front and turn it into a product. And when it takes a form like 1 to the infinity, we know that it will eventually take a form on which L'Hopital's rule does apply. Any questions about taking that logarithm and why we're taking that logarithm? Okay, so now what do we get? Well, we have an infinity times what? A 0. Log of 1 is 0. So what we can do is take this x and throw it in the denominator. I'm gonna actually this should fit if I just keep going straight across. We're going to leave the logarithm in the numerator, put the x in the denominator. X in the numerator is the same as a 1 over x in the denominator, and you can see that. You know, I think it's easiest to see going from here to here multiplied by reciprocal, which is just x. Now, as x goes to infinity, the numerator and denominator both go to 0. So we can apply L'Hopital's rule. And what do we get? Well, what do we get in the denominator? Derivative of 1 over x. Well, negative, or x to the negative 1, apply the power rule. With 1 over x, I like just jumping straight to the fractional form, negative 1 over x squared. And you could write it negative x to the negative 2. I tend to like that form a little more. Negative 1 over x squared. What do we get in the numerator? Well, here, we're going to have a lot of fractions. But we have a lot of space up here, so we can write our fractions very large. We have a logarithm quantity. Derivative of a logarithm is 1 over that quantity. Times, using chain rule, derivative of that 1 plus 1 over x. Derivative of 1 over 1 is 0. 1 is a constant. Derivative of 1 over x, well, there's another negative 1 over x squared. So our derivative of the numerator, logarithm function, derivative is 1 over the inside times the derivative of that inside. Any questions about taking that, or about applying L'Hopital's rule in that step? And now what do we get? Well, we have lots of fractions, but notice we have the same thing in the top as we have in the bottom. We have a negative 1 over x squared. So what does this equal? Well, I'm just going to write it without those fractions. 1 over 1 plus 1 over x. And what do we get as x goes to infinity? We get 1 over 1 plus 0, which is 1. So right on my screen, this is almost at the border. There's nothing written after this 1. That limit is just 1 because 1 over x goes to 0. Any questions about the limit we just computed at the bottom of the board? Okay. We did a lot of work. That doesn't even give us the answer we want, because we didn't compute the limit we want. We computed the limit of some other function. But we can use that to figure out the limit we want by taking exponentials everywhere. Exponentials everywhere. Give us e to the first, and e to the first is just e. I'm not going to write the exponent. Any questions about that one, 1e? Okay, I'm going to mention something about that once we get to 2h. But any questions about 1e? So let's move on to number 2. Number two, we have some derivatives that we need to compute. First, we have what? A function to the 71st power. We have a function to the 71st power. So its derivative, we apply the power rule. Derivative of something to the 71st, 71 of them to the 70th. What are they? X to the -2 minus 5x to the -3. 71 of those raised to the 70th. But then we apply chain rule. Derivative of this inside quantity, -2x, -3, minus 15x squared. So here, if you wanted to write the substitution for part A, it would be u equals x to the -2 minus 5x to -3, dy du 71 u to the 70, du dx -2x to the -3 minus 15x squared. Any questions about part A? Part B, tangent squared of x. Now here we have a squared function because tangent squared of x, that's an abbreviated way of writing. I guess it's not really abbreviated. It's a convenient notation, so you don't have to write all of those parentheses, tangent x squared. Without the parentheses, it may look like, without the parentheses, it would look like that, tangent of x squared, which could be that, which is a different function. But here we have tangent squared x, which is a function squared. The derivative of a function squared, well, just like in part A, we would need two of them to the first. Two tangent x to the first times derivative of tangent x. Derivative of tangent of x is secant squared of x. Any questions about part B? It's a function squared. So the forms of part A and part B, the forms of the final answer should, if you go back and look at these, they should look essentially the same. Now the power rule is applied to get to there, and then the chain rule is applied for this last piece, for this secant squared piece. So any questions about A or B? Part C. Well, part C, y equals x squared 7 to the -x. Well, we have two things multiplied. Derivative requires the product rule. Derivative of x squared is 2x. I didn't write a plus yet. So here we have the first part of our product rule. Derivative of x squared is 2x. What is the derivative of 7 to the x? Well, it's an exponential. It's a general exponential function, an exponential function with a non-e base. Base 7. Derivative of a general exponential is itself times the natural log of the base, natural log of 7. But we have a negative x in the exponent. So we need to use the chain rule. Derivative of negative x is -1. I'm going to take care of that -1 by subtracting rather than adding our two numbers. Any questions about that one? What was that one? 1 or 2C? Okay, 2D. Y is a general logarithm, logarithm of base 2 in this case. X squared minus 4e -2x. So the derivative of a general logarithm looks like the derivative of the natural logarithm, but with an extra constant, in this case, the natural logarithm of 2. Derivative of a general logarithm is 1 over, in this case, x squared minus 4e negative 2x, but times the natural log of 2. And then apply the chain rule. Times the derivative of x squared minus 4 e to the negative 2x, so 2 times 2x plus 8e to the negative 2x. And I'm just going to write that as the one fraction because I think that looks nicer. Now, in these directions, on worksheet and so forth, this is essentially a worksheet. I don't usually say do not simplify your answer. On the test, it will say do not simplify. And with logarithms, you can write them as the one fraction if you have the derivative. Now, the do not simplify is really for, something like part C, where you could factor out an x7 to the negative x, and you could factor out a 2 from the top, but that's, don't worry about that. Any questions about part, what letter was that? D. Part E. Y equals 1 over something to the 7. Well, 1 over something to the 7th is the same as that thing to the negative 7. And we need to take the derivative, so I'm going to write it as that thing to the negative 7th because it'll make it easier to apply the power rule. And also, with one like this, you don't have to eventually write it in a fractional form. You can just leave it like this. The derivative of something to the negative 7th is negative 7 of them to the negative 8th. Then apply the chain rule. 3x squared cosecant x is cosecant x, is negative cosecant x cotangent x. So we have 3x squared minus negative cosecant x cotangent x. Minus negative, of course, is a constant. Now, so for this one, you don't have to write it as negative 7 times 3x squared plus cosecant x cotangent x all over that thing to the 8th. Now, in many ways, it's nicer to leave it in this form because you can see how the answer to part E looks like the answers to part A and B. They both were power rule chain. Any questions about part, what was that, E? Okay, part F, I'm going to do part F up here. Here we need dy dx, but you can't explicitly solve this for y. But what we can do is differentiate implicitly and then apply a chain rule. Dy dx's will appear by chain rule, and then solve for dy dx. Differentiate with respect to x, we get 2x minus 15 y to the 4th, apply chain rule. Because we're differentiating y with respect to x, you need the chain rule, dy dx. Equals on the right side, well, we have x times sine y, that's a product, so we'll need the product rule. Derivative of x is 1. Derivative of sine y is cosine y. But then we have a y there. We need a dy dx. Any questions about getting to that line? so now we need to solve for dy dx. We'll put dy dx's on one side, factor, divide. I'm gonna put dy dx's, I guess, over there. Put the dy dx term over here, bring sine y over there, factor, divide. And we get that fraction. Any questions about that part F? Part G. We have root x plus 1 over the cube root of x to the fourth. Well, we're going to need some power rules with this, so I'm going to write them as their exponent in their exponent forms. Root x is x to the half. 1 over cube root x to the fourth. Cube root of x to the fourth is x to the 4/3. X to the 4/3 in the denominator is the same as x to the negative 4/3 in the numerator. So here, we're going to need some power rules. With x to the half, you get half x to the negative half. Half minus 1 is negative half. Maybe I should put that negative more toward the middle of the fraction. What about the other thing? Well, we have another power rule. Bring the 4/3 down, the negative 4/3 down. X to the negative 4/3 minus 1. Negative 4/3 minus 1. Well, 1 is 3/3. So we have negative 4 minus 3 gives us negative 7. And you don't have to rewrite that, that's fine. Any questions about that one, part G, part 2G? Before going on to part H, it is sometimes in calculus when, maybe not when you're just taking a derivative, but when you're using the derivative for something, it is sometimes convenient to write, square root of x does show up a lot in calculus. So it is sometimes convenient to write the derivative of the square root of x, half x to the negative half, in its fractional form. If you're just taking a derivative, that's not completely necessary. But if you're using the derivative for something, like any of the applications on page 2 of this, then that may be helpful. Part H. Part H, what do we have? We have log x all to the x. Log x all to the x. Well, we have x's in the base and x's in the exponent. And we're taking a derivative. So what we can do is throw a logarithm on this and differentiate implicitly. Logarithm on the left, log y. Logarithm on the right. The x in the exponent comes out front times logarithm of the logarithm of x. So we do have a product now on the right side. Differentiate implicitly. Rid of log y, 1 over y. Apply chain rule, differentiate with respect to x. Rid of y with respect to x is dy dx. How about the right side? Well, we have a product, so we'll need the product rule. Derivative of x is 1. What about the other thing? One over log x, is that right? Might be, let's check ourselves. what do we get for that second piece of the product rule? Well, we need the derivative of the logarithm of x. What do we get? Well, I'm going to write out the u substitution for this. We have a logarithm function. Let's let u be the inside of our logarithm function. So that y would just be then log u. This is a different y than is in part H. So this right here is side work to figure out this second piece. So what do we get? Well, dy dx is dy du, du dx. dy du, 1 over u, u equals log x. So right here we have the derivative for the second piece of our product rule. So is this right? Well, it is, because what do we have here? Product rule derivative of x is 1 times the second plus x times that. X times that, the x's cancel. You're left with 1 over log x. Any questions about getting to that? So now we just need to solve for dy dx, multiply both sides by y. So normally, well, in many cases when differentiating implicitly, in most cases, really in all cases, except for this, y is not an explicit function of x. But in this case, y is an explicit function of x, meaning y equals something with x's and no y's. And in that case, you can write y in terms of only x, so this derivative can be written purely in terms of x. Multiply the left side by y, you get dy dx. Multiply the right side by y, you get y times all of this. And y equals log x to the x. So we get y times all that. We can replace y with this function of x. Any questions about 2h? Okay. So I'd like you to compare 2h and 1e. Now, the original function in both of them, well, the function in question in both of them had x's in the base and x's in the exponent. And we applied similar techniques to figure them out. But the similar techniques we applied aren't necessarily identical. They're identical in the sense that we used a logarithm to help us out. But the resulting calculus and algebra we had to do did look a little different. And to keep them clear, so on exam 2, there was a problem, I believe, like 2h. It was probably 1D. I think number 1 was 20 points. And there was not one like 1E. And some people try to use 1E techniques to answer one like 2H. But to keep them organized, be sure in the back of your mind you're remembering exactly what's being asked. Here, for 2H, all we need is a derivative. All we need is dy dx. So in this computation, there is no mention of limit. A limit is not necessary. We're just taking a derivative and we're using a logarithm to turn into a product, differentiate implicitly, and solve. In one like 1e, we needed a limit. And to figure out the limit, we introduce the logarithm, turn it into a product, and then apply L'Hopital's rule. So with one of these, if one shows up on the final, odds are one or both will. Just keep in the back of your mind, am I doing a limit or am I doing a derivative? Keep that in mind. When you have a limit, you're eventually going to need a L'Hopital's rule with an x to the x, unless substitution works. Any questions about what I just said? Okay, number 3, evaluate each definite or indefinite integral. So for part A, we have a definite integral, which is fortunate because, or we have an indefinite integral, which is fortunate because we have lots of terms, so an eventual substitution would be pretty tedious. X to the fourth, negative 4x cubed, positive 7x, negative 3, negative 5 e to the x, 2e squared, negative pi. So we have lots of terms, but we can do an integral piece by piece. First, we have a power rule. 4 plus 1 is 5. Next, we have a power rule. 3 plus 1 is 4. 4 over 4, negative 1. Or 4 over 4 is 1. So negative 4 over 4, negative 1. Here we have another power rule. Negative 3 plus 1, negative 2. Divide by negative 2, you get negative 7 halves. Raise x to the negative 2. Next, we have an exponential function. E to the x, the derivative of e to the x is itself. So we can also reverse that, carrying the negative 5. And next, we have 2, a constant. E squared, a constant. Pi, a constant. So negative pi, a constant. So you could write the next part as 2x plus e squared x minus pi x. I'm just going to write it. I'll write all the constants together. Yeah, you could do it piece by piece. I'll just write all the constants together. I think that looks a little nicer. Fewer x's floating around. But e squared, remember, e squared is just a constant. So it's not an exponential function where its derivative is itself. It's a constant whose derivative is 0. So going backwards, antiderivative of constant is that constant times x. And then we have an indefinite integral. Indefinite integrals, remember, don't want just an antiderivative. Indefinite integrals want a family of antiderivatives. We had a theorem which said the family of antiderivatives we want all differ by a constant. So the indefinite integral, we need to add a constant, and C is standard. Any questions about part A? So I would like you to note that you can check your work here by taking the derivative. Derivative of constant times x is the constant. Derivative of this is itself. Derivative here, negative 2's cancel. You get x to the negative 3. So negative 2 and negative 2 cancel, positive 7. Here, power rule, 4x cubed with a negative here, power rule, 5 and a fifth cancel. You get x to the 4th. Part B, integral 0 to 1 of root x times x minus 2x squared. Well, first of all, we have a product. We can't just do it piece by piece. There's no product rule for finding antiderivatives. But what can we do here? Well, we can distribute that root x. What do we get when we distribute the root x? I'm going to write over here because this might take up more room. Well, we still have an integral 0 to 1. X times root x. X to the 3 halves. X squared times root x. X squared times root x squared times x to the half. 2 plus a half is 2 1/2, which is 5 halves. And now we can do this piece by piece. what do we get? 3/2 plus 1. Where did that all come from? Is that right? Yeah. Where did that all come from? Well, we have a couple power rules. And remember, with our power rule, we add 1. 3/2 plus 1, 5/2. So we get x to the 5/2 divided by 5/2, which is the same as multiplying by 2/5. So there's the first piece. What about that second piece? Well, same thing, except I just erase all of it. Except we have 5/2. 5/2 plus 1 is 7/2. So you get x to the 7/2 divided by 7/2. That's a 7. Divided by 7/2, same as multiplied by 2/7. But there's also this -2 in front. So throw a -2 over there, that becomes a -4/7. Any questions about finding an antiderivative? Now, the fundamental theorem of calculus part 2 says we can use any antiderivative. So I will choose the one where the constant is 0. Because why not? And here we have 0 to 1. The 0 is kind of nice. That makes it so we don't really have to do anything. But the 1 we do have to substitute. We get 2/5 minus 4/7, all minus 0. When you let x equal 0, you get 0. And 2/5 minus 4/7 is what? 8/35 with a negative. That's 6. What am I doing? 2 times 7 is 14, not 12. How did I get that last thing in one step? Well, because I've done that a lot. But how did I get that in one step? Well, there's an easier way of adding fractions than you may have learned with that whole denominator thing. How do you add fractions? Cross multiply. 2 times 7, 14. Negative. 5 times 4, 20. 5 times 7, 35. So -6/35. It's of course it is equivalent to cross multiplying or to finding the common denominator. You may have to reduce the resulting fraction, but if you have to add fractions a lot, and as you get into Calc 2 and 3, if you're taking those, you will have a lot of fractions you have to add, deal with at the end of problems. Kind of like this one where you had to deal with fractions at the end. It saved me a good amount of time not having to think about denominators, just jumping to the cross multiplication. But if you like the denominators, you're welcome to use them. Any questions about that? Part C. We have an indefinite integral. Integral 8x to the 7th. Oh, it's a 4. Minus 4 cosecant x cotangent x. Well, again, indefinite integral, we can do it piece by piece. Eight x to the 7th, we have a power rule. 7 plus 1 is 8. -4 carries through. Cosecant x cotangent x. Well, the derivative of cosecant x is negative cosecant x cotangent x. So the derivative of negative cosecant x is negative cosecant x cotangent x. We need to make that a positive so that the derivative works. indefinite interval, wants all antiderivatives, add a constant. And I should have done this for part B, but we can in this step check our work, and that's, a lot of the times to make sure the signs are correct with trig functions, I just write one of the signs and then adjust like I did in this one. Derivative here, 8x to the 7th, positive 4 times negative cosecant x cotangent x. So that does work. In part B, what would you have? 2/5 times 5/2 x to the negative, or x to the 3/2, and then negative 4/7 times 7/2 gave you the negative 2x to the 5/2. Check your work. Any questions about part? What was that? C? Okay, part D, integral negative pi to pi of cosine of x with respect to x. Zero. Why is that? Well, you can go through the calculus, you get sine of pi minus sine of negative pi, 0 minus 0. So solution 1 equals sine of x from negative pi to pi. Derivative of sine is cosine equals sine pi minus sine negative pi. Those are the same because pi is the same as negative pi as far as traveling around the circle is concerned. You get 0. That's not the way I did it. Well, maybe it is. Actually, the way I did it was pi is the same as negative pi, so it's 0. Going around the circle. What is another way we could do it? We can compare areas. Here's the cosine function. Where's pi? Where's negative pi? So what do we have here? The integral from pi to negative pi is going to look at, that is showing on the screen. It's going to look at the area above the curve up here in red or green. Yeah, I think that's green. Should have been red. Red and blue happened to be the ones that showed up. That's this one, right? That might be orange. I think it's red. The other one's orange. So here's our cosine function. That's a pretty important part, so maybe I'll draw it less lackadaisically. Okay. Pi is here. Negative pi is here. So the integral is really looking at this area up here and these two areas down here. The area up here is this. Two areas down here are that. But notice both of them are half of one of these cosine lumps, both of the blue ones. So the area in red is the same as the area in blue, and the integral would say that the integral is this area minus that area, which gives you 0. Any questions about that? So either way, you could have gone with that. Another way we could have gone, which is actually more work than both of these ways. So let's do a third solution. So for this week, I gave you a document titled Even and Odd Functions. And it said that for even functions, and it gave 2 examples, cosine x and x squared. For even functions, the integral on some interval symmetric about 0 equals 2. integrals starting at 0. And you can see that with this diagram over here. You know, if we split this at 0, the integral on an interval symmetric about 0 is just going to be this piece on the one side and the piece on the other side. This piece and that piece are both negative. And with this one, you know, using Fundamental theorem, you get 2 times sine x 0 to pi would still give you 0. With this one, that observation may have not saved you much work. Any questions about that? So that's actually a third solution. I should write solution 3. So any questions about that? Let's do, before part E, let's do part D, part 2, I guess. This isn't on the worksheet. So let's call it D with a squiggly line above it to change it. So it's D, that's a tilde, which is used sometimes in math to mean similar but different. Here's D tilde. Let's do this integral. Integral from negative, I want to prime number. 71. Integral negative 71 to 71 of x cubed plus sine x. What do we get? 71 to the 4th. That's mean. You get 0. Why? Let's take sine of x. So sine of x is an odd function, meaning symmetric about the origin. But in particular, the area over here is the same as the area over here. So the integral on, this is just sine of x. So the integral on an interval symmetric about 0, so like we have here, the integral would evaluate to 0 because these areas are the same. One's positive, one's negative. Similarly, x cubed is an odd function. So you can do that piece by piece. Or you could use Fundamental theorem part 2. Any questions about that? So one like part D tilde, you know, if you didn't make that odd observation, the computation would have been rough. If there is one where an odd observation could save you some time, or an even observation, it would be a problem where the computation wasn't rough. So maybe something like this. Pi to negative, or negative pi to pi. Now that computation isn't that bad. So if you didn't make the odd observation for that, then you wouldn't have had to use too much extra time. Part E. Integral 0 pi over 4, 1 sine x over cosine squared of x. Well, we can't do this piece by piece. But what we can do, split the fraction. 1 over cosine squared is secant squared of x. Split the fraction, but keeping in mind which trig antiderivative rules we have. Secant squared of x, we do have one. What about sine over cosine squared? Well, if you had Calc 2, which we don't, well, then you could use a Calc 2 observation. Calc 1 on. What can we do with sine over cosine squared? Well, our rules have derivative of sine is cosine, derivative of cosine is negative sine. This is too much for any of those to apply. But notice here, we have a tangent of x. If we just peel off a sine and a cosine like that, we do have a tangent of x. We have a tangent of x, and we have 1 over cosine remaining, which is a secant of x. So right here, we can reduce that fraction in a way that lets us compute both integrals, or find both antiderivatives piece by piece. Any questions about splitting that integral or splitting that fraction? Derivative of tangent x is secant squared of x. Derivative of secant of x is secant x tangent x. We're evaluating 0 to pi over 4. What do we get, root 2? I think it's root 2. Let's find what we get using side work, and then I'll just write the answer down there. Tangent of pi over 4. Tangent opposite over adjacent, so we get 1. Secant of pi over 4. Secant, well, cosine adjacent over hypotenuse, so secant hypotenuse over adjacent, root 2. Minus what we get at 0. Tangent of 0, 0 over 1, which is 0. Secant of 0, well, cosine of 0 is 1. Flip 1 around, you get negative 1. Or flip 1 around, you get 1. 1 plus root 2 minus 1 is root 2. Any questions about that one? Okay, so the next 10 problems with various applications. And now this isn't all of the applications we've covered. For example, curve sketching isn't on here. I don't know, a couple other things aren't on here. But anything we have covered can show up on the final. So do look at more than just the final exam review. Look at all of the worksheets and homework problems also. Number 4, we have a definition of the derivative question. Definition of the derivative is a nice way to have you compute another limit. So here, we want the definition of the derivative on this. There will definitely be a definition of the derivative question on the test, 100%. And if you don't do the definition of the derivative, you will earn 0% on that problem. Definition of the derivative relates the first third of the semester to the second third. Consequently, to the third third and all of Calc 2 and 3. It's very important. The derivative is actually a limit. Which limit? Well, limit h goes to 0, 1 over, or not 1 over, f of x plus h minus f of x all over h. How can we compute this? Well, lots of square roots are in our way. We can get rid of those. Well, we can get rid of them in a way which will cause our fraction to simplify in a way which makes us the limit computable. A lot of positive signs. We can get rid of the fraction by multiplying by The same thing with a positive rather than a negative. Sometimes called the discriminant, conjugate. Conjugate's a hard word for me to remember, even though it shows up more context. Multiply by that quantity so that the fraction simplifies nicely. What do we get? Well, the denominator, with these, we don't have to factor the denominator, or we don't have to distribute the denominator, I should say. What do we get at the numerator? Well, we get the first thing minus the first thing squared minus the second thing squared. So we get x plus h plus 1 minus x plus 1 minus all of x plus 1. Now what do we get there? Well, the numerator, notice x plus 1 and negative x negative 1 cancel. They add to 0. So we just have h over h times this quantity. The h remaining in the numerator cancels with the h in the denominator. Cancels with the h in the denominator, and we're left with that. And we can now, we still have not taken a limit, but we can now take the limit, let h go to 0. Now, a problem like this, I really don't like blank paper. All these square roots and fractions. Let h go to 0, we get that, and we have 2 of those square root quantities in the bottom. Any questions about that, part A? Part B says, find an equation of a tangent line. Tangent line where x equals 72. So we need a point, we need a slope. Point, when x equals 72, what does y equal? Root 72 plus 1. Slope, derivative evaluated at 72. (72 plus 1) 73. So we get 1 over 2 root 73. We have a point in the slope. We can find an equation for the tangent line. I'll write it down here. Y minus the y value equals the slope times x minus the x value, x minus 72. Any questions about 4? Okay, number 5, find an expression for y which satisfies these two conditions. Well, we have a condition on the derivative. We have a condition on y itself. So we can figure out a general form for y by taking the indefinite integral over here. And then we can find, well, in doing that, we get a family of functions, but we can use this condition to find which specific function we want. So y equals integral of that. Integral antiderivative of e to the x is itself. Antiderivative of 1 is x plus our constant c. And we use this condition to figure out what c should be. But y of 1 equals e. So what does that mean? Well, when x equals 1, y equals e. So e equals e to the 1 plus 1 plus c. Solve for c, e's cancel, c equals -1. And we want an expression for y. So y is that general function, e to the x plus c, where c equals -1. So y equals e to the x plus x minus 1. Any questions about that one? Okay, number 6. That's 73 I wrote that denominator. I like how that looks. And when I write a number or letter, I usually take a picture and file it in my folder of nice letters and numbers. Actually, the 3, I don't really like that. That's 7. I don't know if it shows up on screen, but from up close, that's a pretty nice looking 7. Number 6. Number 6 relates something we did earlier, something we did later in the semester. Approximate this integral. So the area approximation we did was actually an approximation for the integral. We want to approximate this using 3 rectangles. So on a test, on the final, if one of these shows up, you don't have to do both approximations. You can use whichever one you'd like. I'll show both of them because some of you may like one, some of you may like the other. But here we have some function. Well, we know what that function looks like. We're looking at 0 to 2 using 3 rectangles. Interval of length 2 divided into 3 pieces tells us each subinterval has length 2/3. 0 plus 2/3, 2/3, 2/3 plus 2/3, 4/3, 4/3 plus 2/3, 6/3. So we get those x values. Now, what is the left-hand approximation? Left-hand approximation with 3 rectangles. Notice with this curve, our left-hand approximation is an under approximation. Those are the rectangles I drew. Oh, I didn't draw rectangles. Our left-hand approximation would be an under approximation. Not asked, but worth observing. The base of each rectangle is 2/3. The heights are f of 0 plus f of 2/3 plus f of 4/3. What do we get? F of 0 is 1. F of 2/3 is what? 4/9 plus 1. 13/9. F of 4/3 is 16/9 plus 1. 25/9. And what do we get here? Well, we have 38/9 plus 1, 47/9, which gives 84/27. Any questions about that first approximation? So you don't have to find both if you don't want to, but I will find both for this one. 84. 94. 2 times 47 is 94. So any questions about that? But what if you did the right-hand approximation? Well, it would look pretty similar. I'll say 4. 2/3, the right-hand endpoints and over approximations start at 2/3 instead. So we get 2/3 times what, 13/9 plus 25/9. Plus what? What's f of 2? F of 2 is 2 squared plus 1, which is 5. And what do we get? 2/3. Well, again, we have 38/9, but now plus 5, 45/9. 38 plus 45 is what? 83. 83. 2 times 83, 166. Any questions about part A? Well, we did the approximations. We can now, using the fundamental theorem of calculus, find this exact integral. And we'll notice our exact integral will give us a number between those two. What do we get using fundamental theorem? Well, the integral, an antiderivative, I should say, of x squared, power rule, third x cubed, derivative of x is 1. Evaluate from 0 to 2. Evaluate at 2, you get 8/3 plus 2. Evaluate at 0, you get 0 plus 0. So here we get 14/3. 14/3 is what? It's like 5, or it's 4 2/3. So our answer should be on both sides of those. 27 times 3 is what? 101? No, what am I saying? 27 times 3 is 81. So this is a little more than 3, which is less than our exact answer. 27, that's a little less, a little more than 27 times 5. 27 times 5 is 135. So here we have an answer a little more than 3, an answer a little more than 5, and they are on both sides of the exact area. So those are consistent with that observation. Any questions about number, what was that, 6? Okay, number 7. A plane flying horizontally at an altitude, that's the bad racing, at an altitude of 1 mile and a speed of 500 miles per hour passes over a radar station. Find the rate at which the distance from the plane to the radar station is changing when the plane is 2 miles from the station. Standard related rates question. The plane is flying horizontally. Okay. Passes over a radar station. There's our radar station. Flying 1 mile in altitude. So that distance is 1. And the question is, find the rate of the distance from the plane to the radar station. Well, the plane is traveling on that line, so it's traveling horizontally. So in particular, this distance is variable. The distance from the plane to the radar station is variable. Let's call it x. Find the rate at which the distance, oh wait, I said the distance from the plane to the radar station is variable. It is variable. Let's call that y. The other variable in this case would be the horizontal distance the plane has traveled, since going directly over the radar station. So let's call that x. So we have our two variable quantities here. And the question says, find the rate at which the distance from the plane to the radar station. Find the rate at which y is changing when the plane is 2 miles from the station. So this question wants us to find dy dt, how y is changing as time is changing. When what? Well, dx dt of horizontal change is 500 miles per hour. And what else? Well, when y equals 2, it says when the plane is 2 miles from the station. When y equals 2, x is √3. From our 1 to √3 to 2 triangle that we've seen before. Or you could say Pythagorean theorem, 1 squared plus x squared equals 4, so x equals √3. But we need here an equation. Fortunately, Pythagorean theorem gives us an equation. Differentiate with respect to time. X and y are functions of time. So by chain rule, dy dt, dx dt are going to be showing up. Derivative of y squared with respect to time is 2y to the first, dy dt. Derivative of x squared with respect to time, 2x the first times dx dt, since x and y are both functions of time. Those rates are non-zero. Now we just need to substitute. dy dt is here. Notice first, I'm just going to erase them. There are 2's everywhere. We don't have to worry about those 2's. So y equals 2. When x is √3, well, when y is 2, x is √3. dx dt is 500. Solve for dy dt, divide by 2. I have circling answers. 500 divided by 2 is 250. Any questions about number 7? Number 8, find the absolute maximum, absolute minimum of this function and where they occur for that function on the interval 0 to 2. Well, the extreme value theorem will give us what we want. What does the extreme value theorem tell us? Well, it tells us the absolute maximum, absolute minimum will occur either at an endpoint of 0 to 2 or at a critical point. Critical points are where the derivative is 0 or undefined. So let's find what the derivative is 0 and where it's undefined. Derivative 3x squared times 2/3, 2x squared minus 3x minus 5. And we want where this equals 0. We want where this is undefined. So hopefully a factor, so we don't have to use quadratic formula for completing the square. And if you have one in this class with me, we'll factor. Unless it was one of us from before. How does it factor? Well, we need numbers that what will make 5 and 3. 5 and 1 make 5. They're the only way to make 5. What if we put a 5 here and a 1 there? Well, that's not making 3. So what if we put a 5 here and a 1 there? Well, that looks like it could make -3 if we make it -5x, positive 2x. When does that equal 0? When x equals -1, or when x equals 5x. What was our interval? 0 to 2. Nice. So our absolute value, absolute minimum will occur either at endpoints or critical points. But notice neither of those critical points is within the interval 0 to 2. So we don't even have to think about that. All we need are the 2 endpoints. F at 0 is 2. F at 2 is what? 16 thirds. -6. -10. +2, which gives us what? 16 thirds minus 14. -26 thirds. The largest is the maximum, the smallest is the minimum. So here's the absolute minimum or maximum. Here's the absolute. Any questions about that one? So if the critical points aren't within the interval, then they don't matter as far as finding the maximum and minimum on that interval is concerned. If a ball is thrown vertically upward with a velocity of 80, then its height off the ground is that function. 3 questions. At what time does the ball reach its highest point? Well, what happens at its highest point? Well, the derivative is 0. With velocity, you could say at its highest point, the position is no longer changing. So the velocity is 0. Either way, we're setting velocity equal to 0. So we need a velocity function. Derivative of position, 80 minus 32t, set it equal to 0. 80, 30 seconds, which reduces to what? 40 sixteenths, 20 eighths, 10 fourths, 5 halves. So 5 halves seconds. Any questions about part A? Part B. What is the maximum height reached by the ball? Well, at its highest point, its velocity is 0. At 5 seconds, it's at its highest point. We want the position at its highest point. Position at time 5 halves. S at 5 halves. Five halves squared. 25 fourths. 80 times 5 halves is 40 times 5, which is 200. 16 times 25 fourths is 4 times 25, and there's a negative. So the highest point reached by the ball is 100 feet. Any questions about that? Part C. At which value does the instantaneous velocity equal the average velocity? On 1 to 3. Guess I'm not going to fit that on the bottom of the board. At what point, at what x value or time value, does the instantaneous velocity equal the average velocity on 1 to 3? Well, first we need the average velocity. The average velocity is the change in position divided by the change in time on the interval 1 to 3. What is position at 3? 240 minus 144, 96. What is the position at 1? 80 minus 16. 80 minus 16, yeah, that is what I said. 80 minus 16, 64. So the top is 32, the bottom is 2. So the average velocity on the interval is 16 feet per second. So this question says, well, any questions about finding the average velocity? This question asks, at what time does the instantaneous velocity equal that? Well, the instantaneous velocity is given by velocity function evaluated at any t value. So we want where that equals 16, the time at which that equals 16. So we have 80 minus 32t equals 16. Solve for t. T equals 2. 80 minus 64 is 16. Any questions about that? Notice that that t value is between 1 and 3, which is expected by the mean value theorem. Well, it's expected that you will find one between 1 and 3 by the mean value theorem. You know, there could be others beyond that for other functions. Or before that. So any questions about, what was that? 9? 10. Find the positive number such that the sum of it and its reciprocal is minimized. Optimization. Find the positive number. Well, let's call it x. Find x. What does the question say? Such that the sum of it and its reciprocal is as small as possible. Such that x plus 1 over x is minimized. Well, we have our function. Find positive x, it should say. Well, let's call it s. S is a sum. We know that the maximum or minimum will occur at a critical point. If we had a clear closed bounded interval, it could be an endpoint, but we don't. X can be anything from 0 to infinity, non-inclusive. Derivative here, derivative of x is 1. Derivative 1 over x, well, here is one of those where I like jumping straight to negative 1 over x squared. Because we have to do some work with this. We need where it's 0 and undefined. Let's set it equal to 0. 1 equals 1 over x squared. Multiply by x squared. X squared equals 1. Gives us x equals positive 1. Technically, or negative 1, but note, well, maybe I'll say that. Technically positive or negative 1. But this question says only positive x values. So we don't need to worry about negative 1. Notice that the derivative, we also would have to find where it's undefined. It's undefined at 0, which is also not a positive number. So where it's undefined actually doesn't matter in this case. But we have a candidate, x equals positive 1. Does x equal positive 1 give a maximum or a minimum? Well, let's check using the second derivative. So x equals negative 1, or sorry, x equals positive 1 gives a, I'll fill in the blank in a moment. I won't go off screen. Why? Well, what's the second derivative? 2 over x cubed. Two over x cubed. Where's that come from? Well, the derivative here is 0. There we have negative x to the negative 2. Derivative x to the negative 2 is negative 2x to the negative 3. Negatives cancel. You can just write that as 2 over x cubed. When x equals 1, that gives us a positive number. X equals 1. This is positive. The function is concave up, which means our critical point will give us a minimum. X equals 1 gives a minimum, which is what we wanted. So that is the value such that x plus 1 over x is minimized. Any questions about that? Notice the minimum sum is 2. The question doesn't say find the minimum sum, it just says find the value. Any questions about that? So number 11 is another type of optimization question. Odds are more likely you see one like 10 possibly than one like 11. But the same approach applies. The rate at which photosynthesis takes place, this is from a textbook, these aren't my numbers. The rate at which photosynthesis takes place for a species of phytoplankton is modeled by this function. Must have been fun to find this function. Where I is the light intensity measured in thousands of foot candles. For what light intensity is P maximum? So this question says, maximize this function. Well, we'll follow that same approach. We'll maximize this function. P prime, quotient rule, bottom, derivative top. Minus top, derivative bottom, over bottom square. We want where this is 0, we want where it's undefined. Well, let's simplify the numerator a little first. I'm going to go up here. 100 I squared plus 100 I plus 400 minus 200 I squared. What did I write wrong? How did I know something was written wrong? Well, we shouldn't have gotten the same exponent. That's what I wrote wrong. The derivative of I is 1. So here we are, notice I didn't say it, we are, our variables I differentiate with respect to I. Same thing. I and 1 are very similar. 1. Minus 100 I. All over the denominator. Yeah, okay, I'll write the whole denominator. What does this reduce to? Well, oh, that's nice. 100I and negative 100I cancel. So we're left with negative 100I squared plus 400. Nice, we get 2 and negative 2. That's convenient. So you get negative 100I squared plus 400. Any questions about simplifying that numerator? We want where this is 0, where it's undefined. Zero when x is x. See, I'm very used to doing calculus with x. Equals 0 when I equals positive or negative. If you set the numerator equal to 0, you get 100I squared equals 400. Divide by 100, I squared equals 4. I is positive or negative 2. And we also need where it's undefined. This is never undefined. It's undefined where the bottom equals 0. Use the quadratic formula, you'll get complex numbers, imaginary numbers, I should say. So yeah, I guess this is what, 3 problems after I said you never have to use quadratic formula. Well, on a test, you won't have to use quadratic formula. Keep that in mind. But here we have 2 possible candidates. Which one will give a maximum? Well, let's see. we could take the second derivative. The second derivative, kind of messy. I'm going to use the first derivative instead. How can we show we get a maximum? How can we show it gives a maximum? By showing increasing to decreasing. We can use the first derivative for that. So if the first derivative is positive on the left, negative on the right, then that works. The sign of the first derivative on the right, on the left, let I equal 1. Let I equal 1, you get positive over a positive. Which is positive. Let I equal 3, you get a negative over a positive. So at I equals 2, at I equals 2, at I equals 2, we get a maximum. You could have taken the second derivative, shown concave down. This probably is easier with this function. So we get our maximum. Light intensity, I don't believe can be negative. So I'm just going to say positive too. Any questions about that one? So these optimization questions, there are many types of things you can optimize. My main reason for putting one like this on this worksheet was to show there are many kinds of functions that you can optimize. I have also asked one in the past on a worksheet, not a test, about, I don't remember, some sort of physics thing. And it's the same basic setup. You can compare the work for this one to work for other optimization questions. It really is the same. Find where the derivative is 0 and show that it gives a maximum or a minimum. But any questions about that? So here, number 12, we have another derivative question. Here we're going to need the first part of the fundamental theorem of calculus, because we can't apply the second part. And what does the first part say? Well, the first part says that the derivative of a definite integral from a number to x is given by the integrand evaluated at x. So here, we can make a u substitution so that the first part applies. F prime of u, using the first part of the fundamental theorem. Oh, I should have written what u is. Let u equal that x to the fifth quantity. Then f prime of u is what? Well, first part of fundamental theorem calculus says it's tangent of u cubed. Then f prime of x is given by the chain rule. Given by the chain rule. Du dx times df du. Tangent of u cubed times 5x to the fourth. U to the fifth, 5x to the fourth. And we can just rewrite that with u, or with x as for u. X to the fifth to the third is x to the 15th. You could have also done that without writing out u substitution if you want. Any questions about number 12? Number 13 covers our week 6 topic, the net change theorem and a similar observation giving a total distance traveled. But when our integrand measures a rate of change, the second thumb alternative of calculus will give us a change in whatever the rate is of. In this case, velocity is the change of position, so the net change theorem will give us a net change in position. Particle travels with this velocity on the interval, we want 0 to 5. Find the net displacement, total distance traveled, on 0 to 5. Well, the net displacement is given by what? Well, the integral from 0 to 5. They should have made it like 0 to 2, so the numbers are a little easier. That's okay. Integral from 0 to 5 is what? Well, 36t minus the third t cubed from 0 to 5. What do we get? Well, 36 times 5 is 18 with 0. Because half of 36 is 18. So we get 180 minus 5 cubed, 125, divided by 3 at t equals 0, you get 0. And what does this equal? 415. Yeah, 18 times 3 is 54. Any questions about the net displacement, the net change in position? Maybe I should throw units on it. Nope, I didn't. If I gave units, I could have thrown units, but I didn't. So any questions about net displacement? Now, an integral, remember, treats quantities below the x-axis as negatives and quantities above as positive, meaning walking backwards is treated as a negative, which is why the integral will give us a net displacement. It'll factor in the walking forward and the walking backward. And the walking backward is negative, walking forward is positive, so walking backward will cancel its own walking forward. But if we want to count the negatives, which we do for total distance traveled, we can do that by taking the absolute value of our velocity function. What do we get here? Absolute value of 36 minus t squared. Well, how do we do that? Well, we're going to need where the curve intersects the x-axis, because that's where the absolute value is going to split into pieces. But notice here, t-axis, not x-axis, that our velocity function intersects the x-axis, the t-axis, at time 6, which is beyond the interval in question. Which means that this absolute value is not going to split into 2 pieces on this interval. Okay, we didn't even necessarily have to do this if you wanted to graph it using a graph transformation, kind of like I did here. But this intersects the t-axis, t equals 0, off of that interval. So all we need to do is figure out if this piece is positive or negative on this interval. In this case, it's positive. You can let t equal 1, for example. 36 minus 1 squared is positive. Uh, 36 minus 1 squared is positive. So on this interval, 36 minus t squared is positive. The absolute value simplifies to itself. You can see that with this sketch, which actually was a sketch of this curve. And this integral is the same as that one. So we get 415 over 3. So you can see for one of these, when the entire velocity function is positive, these quantities do equal the same thing. On the week 6 worksheet, there's one where it goes through the x-axis, and you are definitely encouraged to look at that. But a graph observation like this did make this computation a little simpler. Any questions about anything we just covered on the review document? Okay, any